This example problem is going to involve several key ideas involving work, energy, and power. In this problem, we have a box that slides down a ramp. There's friction on the ramp, and the force of friction is going to be big enough to make the box stop. So it's initially moving and it's going to slow down and stop. And we're going to look at how far the box slides. We're going to calculate the work done by friction, the work done by the normal force, the work done by the force of gravity. And we're also going to look at power. There's two types of power we're going to look at. We're going to look at the instantaneous power at one point in its motion, specifically halfway between its initial and final positions. And we're going to look at the average power generated by friction from the very beginning to the end. So, to go through and do this problem, the first thing that we're asked to do is find how far the box slides. And probably the easiest way to do this, because all of the forces are constant, is to go through and calculate the acceleration, use kinematics, and calculate this distance. This is also going to be helpful because to be able to find the instantaneous power and the average power later on, we're going to need that acceleration to be able to find some other quantities. So if we look at this, if we have this box on the ramp, it has a mass of 16.2 kilograms. The force of gravity acting on it is the mass times 9.8, which is 158.76 newtons. So we can break that force of gravity into components. So we have the component that's perpendicular to the ramp and the component that's parallel to the ramp. This parallel component of the force of gravity is 97.7424 newtons. This perpendicular component of the force of gravity is 125.105 newtons. We also have the normal force acting on the box. The normal force is going to equal the perpendicular component of the weight. So it's also 125.105 newtons. And finally, we have the force of kinetic friction acting on the box. That force of kinetic friction is the coefficient of kinetic friction times the normal force. Here we're told that the coefficient of kinetic friction is 1.2. And we just found that the normal force was 125.105 newtons. So this force of friction is 150.126 newtons. Okay, we're told to let down the ramp be the positive direction. And so the net force, the forces perpendicular to the ramp, balance out. So my net force is the force down the ramp, which is the parallel component of the force of gravity, positive 97.7424 newtons, plus the force of friction, but that's up the ramp, so it's negative 150.126 newtons. And so this net force is negative 52.384 newtons. So to find the acceleration, the net force is the mass, 16.2 kilograms, times the unknown acceleration a. So we get that the acceleration is negative 3.2336 meters per second squared. The negative sign here means that the acceleration is up the ramp. So to find how far the block slides, it starts at a position of 0. We're trying to find where it ends up. The initial velocity we're told is 1.47 meters per second. So that's given in the diagram. The final velocity is 0. The acceleration is negative 3.2336 meters per second squared. And we don't know the time. We are going to find that time later on, but right now we can look at an equation that doesn't involve time. So we have the equation that relates the velocity to the position. So the final speed of 0 squared equals 1.47 squared plus 2 times the acceleration, negative 3.2336, times the final position, x minus 0. And if we solve that for x, we get 0.33413 meters. So that's part A of the question. How far does the block slide? It slides 33.413 centimeters, or 0.33413 meters. Okay. The next thing that we're asked to do is calculate the work done by friction, and then the work done by the normal force, and then the work done by the force of gravity. So to find the work done by friction, the work done by friction will be, first of all, negative, because the force of friction is up the ramp, the motion of the box is down the ramp, and it would be the force of friction, which is 150.126 newtons, times the distance that we just calculated of 0.33413 meters. And so the work done by friction is negative 50.1616 joules. So friction is taking energy away from this box. That's what negative work is. It's something that removes kinetic energy from an object. Part C was the work done by the normal force. In this case, the work done by the normal force is easy to calculate. It's just 0 joules. The normal force is perpendicular to the motion of the object. If a force is perpendicular to the direction an object is moving, that force does 0 work. Work is the parallel component of the force times how far it moves. And so if it's perpendicular, there's no component that's parallel, and so the work done is 0. Part D is asking for the work done by the force of gravity. And often when we calculate the work done by gravity, we would do the gravitational force times the vertical distance that it moves. In this case, rather than going through and calculating the vertical distance it moves, we know how far it moves along the ramp. That was that distance x that we found. And so we can look at this parallel component of the weight. And if we take the parallel component of the weight and we multiply it by the distance, that's going to give us the work done by the force of gravity. So the parallel component of the weight was 97.7424 newtons. The distance, again, is 0.33413 meters. The work done by gravity is positive in this case because the force of gravity is down the ramp. The motion of the box is down the ramp as well. So this work done by gravity is positive 32.6587 joules. Okay, so part A involved kinematics. Parts B, C, and D involved calculating work, so is the force times the distance. Part E and F, we're looking at power. So E wants the instantaneous power halfway between the initial and final positions, the instantaneous power generated by friction. And part F is asking for the average power generated by friction from the start to the stop. And so for part E, the first thing that we need to do is we need to know where halfway between the starting and ending positions is. So it's not asking for half the time to go down the ramp. It's saying that it's traveled half of the distance. And so halfway down means it's the 0.33413 meters over 2. So we're looking at the point that is 0.167065 meters down the ramp. So instantaneous power is the parallel component of the force, the component of the force that's parallel to the motion, times the velocity of the object. It's how quickly work is being done at any instant. Work is force times distance. Work is F times x. The instantaneous power, you're taking the derivative of that work with respect to time. If the force is constant, then it's F times dx dt, which is the velocity. So this means that we need the velocity halfway down. So it's starting at a position of 0 meters. The later position is 0.167065 meters. The initial velocity is still 1.47 meters per second. We're looking for this final velocity. The acceleration is still negative 3.2336 meters per second squared. We don't care about the time here. So to find this velocity, again, I can use the equation that relates the velocity to the position. So I have that the unknown final speed squared equals 1.47 squared plus 2 times the acceleration times the distance of 0.167065 meters. And so if you solve this for the speed, you get 1.03945 meters per second. So it's slowed down a little bit. It's gone from 1.47 meters per second down to 1.03 meters per second. It's only lost a small amount of its energy, or of its velocity. It's about 2/3 of what it was at the beginning. So now, for the instantaneous power generated by friction, first of all, the force of friction is opposite the direction it's moving, so this instantaneous power would be negative. And I would take my force of friction, which I calculated earlier was 150.126 newtons. So again, that's what I calculated all the way up here. I found the force of kinetic friction, and I multiply by the velocity that I just calculated, 1.03945 meters per second. So that gives me negative 156.048 4.85 watts. So that means that friction is taking away 156 joules per second right at that point. Again, at the beginning, when it's moving faster, friction is taking away energy quicker. At the end, when it's moving slower, it's not traveling as big of a distance in the same amount of time, and so friction is taking away energy at a smaller rate. Now, in this question, it asked for the magnitude. The magnitude means the absolute value. So that would be 156.0485 watts. Again, power is a scalar, so magnitude is just the absolute value of the quantity. The final part of the question asks for the average power generated by friction. What is the magnitude of the average power generated by friction from start to stop? So again, magnitude, in the end, we're going to have a positive number. We're going to take an absolute value. But we want the average power generated by friction from start to stop. So average power is the amount of work done divided by the time that it takes. So again, instantaneous power is exactly what's happening at one moment in time. It was at the time that it was at the point halfway down when the velocity was exactly 1.039 meters per second. Here, we want the average power. And so we want to look at the overall amount of work done from the beginning to the end by friction only. But we also need to know the time that it takes from the beginning to the end. And so this is, again, one of the reasons why it was important to have the acceleration. So again, we know that it started at a position of 0 meters. The later position was 0.33413 meters. Again, this is not halfway down, this is all the way to the end. I know that it started at 1.47 meters per second. I know that it's ending at 0 meters per second. I know that the acceleration was negative 3.2336 meters per second squared. And I'm looking for the time. So I have several methods that I could calculate the time. The easiest is to just use velocity as a function of time. The other one would involve using the quadratic formula if we looked at position as a function of time. This is much easier to solve. So we have 1.47 meters per second plus negative 3.2336 times t. And we get that the time to go down the incline, the time that it takes to stop, is 0.4546 seconds. So this means that the average power generated by friction would be the work done by friction which is what we calculated in part B. It was negative 50.1616 joules. Again, we wanted the work from the beginning to the end because we're looking for the average power from the beginning to the end. So it was negative 50.1616 joules divided by the time of 0.4546 seconds. So that average power is negative 110.342 watts, or the magnitude of it just means the absolute value, so it'd be 110.342 watts. So friction took away, on average, 110.34 joules of energy per second, which is different than the power that it had halfway down. Again, it's saying that right at that instant, it was taking away 156 joules per second. This only asked about the power generated by friction. We could have looked at the average power or the instantaneous power for the force of gravity. Again, the instantaneous power when it was halfway down, it would have been that parallel component of the force of gravity times the velocity halfway down, the 1.03945 meters per second. In that case, the instantaneous power generated by the force of gravity would have been positive. Again, for that, we would only take the component of the force of gravity parallel to the motion, that parallel component that we had, the 97.7424 newtons. If we wanted the average power due to the force of gravity, we would take the work done by the force of gravity, the 32.6587 joules, and we would use the same time, the 0.4546 seconds from beginning to end. So again, there's a lot of other things that could be asked about this, but this problem ties quite a few things together. It's a very good problem. It's one that you really need to make sure that you understand all of the key ideas for, because it really helps you understand how to use kinematics and work and energy and power and how to tie all of the things together.